So yeah, thank you so much for having me here today to talk about urine recycling. I had hoped to come down in person, and for a number of reasons, I wasn't able to today. So thanks for the event organizers for figuring out how to get me in on Zoom. I'm really glad to be here, and want to tell you just a few things about how our program has been working for the last 12 years, what we've been doing, what we've learned, and share some aspects of it that might be particularly relevant or useful to you all on Cape Cod. So first, the biggest fact about urine, why we focus on diverting that, has to do with volumes and concentrations. So this little dot over here, can you see my little cursor when I move it around? Does that pointer work? Great. So this little dot is the volume of human waste. It's less than a gallon per day of urine and feces combined, most of the urine. This is the volume of water we flush down various drains every day, about 60 gallons per day. So about 120 times more water than urine. However, urine has, as Hilda and Earl mentioned, about 3/4 of the nitrogen. Even though it only makes up this tiny sliver of the volume, it makes up 3/4 of the nitrogen content, about 2/3 of the phosphorus content in all of our wastewater. So taking this tiny sliver of yellow out has the effect of taking these huge pie wedges of nitrogen and phosphorus out of the wastewater if we can do that. So how can we do that? At the Rich Earth Institute, we have set up over the last 12 years a system with people in their homes and businesses, ourselves who transport the urine and manage it, and then farmers who receive it and apply it to their fields. And these are separate categories of collection, transport, treatment, and application. And I'll show in other slides the individual breakouts of these things. But I wanted to have the first slide just show you the whole process in one view. If you want to see this in more detail or look at it later or see all the supporting information, this link at the bottom, richearthinstitute.org/urine diversion guide, is a downloadable PDF. You can also just navigate to our site. It's under publications. But essentially, we have urine being collected either in inexpensive portable systems or in plumbed systems that then go to either a drop-off location for the portable containers or larger containers for pump out. Our truck comes and takes out the urine either from the depot or the tank that's at a home, brings it to, in our case now, a treatment center. We process it and then bring it by truck to the farm. And our whole process for that is about a 12-mile process. So it's not a lot of transport, but like as Hilda was saying, it's not very expensive to transport because it's not a very large volume. So it could be a larger distance if it had to be. So drilling down into the specifics, this is the informal, low-cost, inexpensive way to start collecting urine. This is not the end-all and the be-all, but it is the way that many of our participants have started out just trying urine collection. It's a 5-gallon screw-top container. We build these funnels out of commercially available parts, makes a sealed column. A little round ball goes in there to seal off any odors. You can add vinegar to totally eliminate odors. And then you either urinate it into directly, or you can empty any container into this funnel to collect the urine. And this little ball floats up and then settles down to hold in the odors. Someone who's using this system, then, here are a bunch of them we took a picture of that we sent down to Cape Cod. So these are out in the community at various homes on the Cape. And they're available from us as well. We make them, we sell them online, and we also can arrange for larger shipments because they're rather expensive to mail these things. But we've sent a bunch to the Cape over the last year or two. Once the container is full, in Brattleboro, you go to one of our 2 depots. And that's a location where you enter a little building. We just rent a little part of a larger storage building. You enter into it. This device is what you use. It's a pump out station, a vacuum pump out station. So you place your jug down here on the white square, pull down the handle, and this wand goes into the open mouth of the container. You can see it again pictured right here. And a vacuum pump automatically switches on. There's a little switch in here, and it sucks the urine under high vacuum into the vacuum chamber, which then dispenses it down into one of these interlinked tanks, which can then contain 1,500 gallons of urine before we have to come pump it out. So it's a very nice interface because this vacuum pumping system totally pumps out the jug. You're left with an empty jug that you can then take home and add a little more vinegar if you're using vinegar, and then refill. And so that's this approach. It's very easy to get started with as a user, obviously, because you just take one of these home and you use it. But it does require you to transport and pump out your tanks, which isn't bad. But over time, people can want something more hands off. And so that's where these permanently plumbed systems came in. These are some of the same systems you saw in the previous presentation, but these are the ones that we have direct experience with in Brattleboro. The Wostman Eco Dry, which has it's a urine diverting composting toilet. So the solids still go into a compost bin. Urine goes into a small jug or a large container. That does complete separation of human waste. The Eco Flush flushes toilet paper and feces while urine goes through this drain to a tank on site, which we then pump out. Or the Laufin Save toilet, which I like a lot, and we're working on becoming importers of these. This is European. These are both. All of these are European, but this is one that recently won a design award in Milan because it has this invisible trap. Urine flows down the front part of the bowl, goes around a tight corner. Surface tension brings it around into the urine trap and the urine drain, while flush water shoots over at higher velocity, does not cling to that edge, and carries solid waste down and out of the toilet. So it's a nice way to avoid getting much flush water, and the user doesn't necessarily even know it's urine diverting. It just looks like a designer toilet. So we also have two options that are not toilets. They're urinals, but they're sit-down urinals. This is the Cinderella. We have one of these that we are looking forward to installing soon, but haven't quite yet. We just got it. It's a sit-down toilet, but you should only pee in it. And then the pee pod that the Green Center is working on is also a urinal that folds out of the wall. We have one. We have the predecessor to this in Brattleboro in a couple of locations, and it's very popular, but that one is out of production. So I'm excited that there's a new one coming into production. Our service looks like this. We show up with this truck you see down here. This is Arthur Davis, who runs our urine collection operation. And we just connect a vacuum hose to a port that we've installed on the outside of the building. It sucks the tank dry. The tank is in the building, in the basement. We suck that dry. Comes out this hose as far as it needs to go into our dedicated urine-only truck. We have a waste hauling permit for that. And so then we are able to then bring it back to our treatment facility in this truck, which can haul 1,000 gallons at a time, which is about the total output of 8 people over the course of an entire year. We have a vacuum pumping system and a gas transfer pump, so we can quickly pull that urine up out of a tank and put it into our onboard tanks and bring it to the research center. And then once we're there, we do pasteurize it in this pasteurizer developed by Brightwater Tools, the spinoff of the Rich Earth Institute. And then we store it in large tanks. We have some above ground, some underground tanks outside. This is our research center where we do all of our research and our urine processing. And this pasteurization is necessary because it's coming from urine diverting toilets. There could be some amount of solid waste that ends up with the urine. If people, someone used the toilet, a little bit of fecal material gets in the front, there could be fecal pathogens. So we pasteurize everything that complies with our state permit, and it protects everyone in the chain. If you are only using pure urine, that's I believe what Earl and Hilda were talking about. Those actually aren't our recommendations. It's from the World Health Organization, and we've republished that in some of our publications. So we do have printed material that says that, but the World Health Organization has guidelines that say that if it's just pure urine, not urine and feces, but just pure urine, then that can be used for home consumption without further treatment. But again, we pasteurize because that then makes it essentially a commodity that can be used without restriction on any kind of food crop by anybody, without any potential risk. And that is all. That's all we need to do in order to make it a fertilizer that we then bring out to farms. But there is an additional step that we've been working on because we think that it has a lot of potential for reducing the transport and storage costs and easing the amount of work it is for farmers to handle and apply the fertilizer. And that process is concentration. It's freeze concentration. And this is a process that started out at Rich Earth Institute as a basic research project. We were funded by the National Science Foundation to develop a treatment train for turning urine into fertilizer. And we tried reverse osmosis to squeeze the urine down, squeeze out the water, retain the nutrients, make a concentrate. But those membranes are pretty easy to foul with solid material that's dissolved in the urine. So we didn't pursue that. We went to freeze concentration, which is the process of partially freezing any liquid. The ice that is formed is pure water. And then all of the unfrozen liquid contains all the solute, everything dissolved. So all the nutrients, all of the potassium, nitrogen, phosphorus that were in the urine stay in that small amount of unfrozen liquid. We can drain that out and have a concentrated fertilizer up to a factor of 10 concentration or a 90% reduction in volume. And this is a product Brightwater Tools is developing for sale to treat urine, and we're hoping to supply a beta unit for use on Cape Cod if that's useful in terms of reducing the volume, because it is practical to store and transport that urine, but it is even less expensive and even more practical to store only 80% of the volume, say, of that original urine. In any case, once we've processed it to the extent that we're going to, we take it to a farm. This is urine being applied on hayland. So this is hay that's been cut once. Now it's growing. It needs more fertilizer in order to grow again. And this is one of our partner farmers applying a 500-gallon batch of pasteurized urine to that hay. And it takes about 1,000 gallons of this urine to fertilize an acre of hay. So farmland can absorb a lot of urine in a productive way. If this had been concentrated by a factor of 5, say, then it would only take 200 gallons of urine to fertilize the field. Same amount of field fertilized by one person, but less material transported to the farm in order to accomplish that task. So the obvious question then is, well, what's in the urine? How much nitrogen is in there? And how do we know that it's a good fertilizer? And how do we know how much to apply? And so we do regular testing of our collected urine and the fertilizer product we make. And we find that it almost always has between 5,000 and 6,000 milligrams per liter of nitrogen. And by comparison, that's about 100 times stronger than typical wastewater, which might have around 60 milligrams per liter. It can range, but somewhere in that range. So it's about 100 times more concentrated, which is what we'd expected, what I told you at the beginning, actually. So that is borne out by third-party laboratory tests. So that's the concentration, but how much do you actually get from a home? And if you're trying to remove nitrogen from the wastewater system, how do you know how much you've removed? We've followed 5 different households over a 1 to 6 year pumping history. And these are the compiled statistics. And it also translates into what's the value of what's been collected. So we had 5 homes, average of 3.1 people per house. Each house collected on average close to 300 gallons of urine, which, sorry, that's been happening all day. I'm getting emergency alerts about Massachusetts 911 system being down, even though I'm in Vermont. I'm not sure why. So sorry about that buzzing. So about 14 pounds of nitrogen per house per year. And using figures from a study that was done by the state of Massachusetts, looking actually specifically at Cape Cod, the cost of sewering or IA systems, we used the figures from that study in terms of what it would cost to remove nitrogen per pound removed. And the value of removing those 14 pounds of nitrogen is between about $4,000 and $10,000 per household per year. So that's essentially what it would cost to use a sewer or an IA system, high range, low range of both those, the extremes. What's the range it would cost to remove that 14 pounds via IA system or sewer? It's many thousands of dollars per year, which of course is much more than it costs to just collect urine and have it hauled away and brought to a farm. Per person, that's about 90 gallons, about 4 pounds, and that's $1,000 to $3,000 is the per person. These are the averages, but let's look at the actual the amounts per house or per person, because there's wide variation. And this is the case in the urine we collected. This would also be the case if you were looking at what was sent to an IA system or sent to a sewer from the house. I'll get into why, but it has to do with how many people are in the house and how much they're home. And urine diversion is particularly suited to deal with this variation, which I'll get to. But before I get there, I want to show you how much variation there is. In this graph, these are the 5 households that we studied. And you can see 2 people in this house, 2, 3.5. The number of people changed partway through the study. 4 people, 4 people. If it were the same amount of urine per person, this would be, a nice stepped graph. But you see a lot of difference between 2 2-person houses and a lot of difference between these 2 4-person houses. This 2-person house actually collected more urine than this 4-person house because these people, presumably they weren't home very much, and these ones were home a lot. These 4-person household collected more than twice as much as that one. I happen to know these 4 people are home almost all the time. So a lot of things you don't know just by the demographics or the counting houses. It's also interesting to see that the amount of nitrogen per person per year. So this is not per house. We're still looking at what happened in the houses, but we're looking to see in house 2, they actually collected 3 kilograms, which is over 6 pounds of nitrogen per person per year. Whereas this 4-person house, it had a reasonable amount of urine collected, but per person, it actually wasn't very much urine or nitrogen. The reason I'm showing you this is because with urine diversion, if you want to quantify nitrogen removal, you can actually measure it directly. And and what that means is, well, I'll cycle back to this slide after I explain some of the other context around it. So I want to compare urine diversion and how we measure nitrogen removal from urine diversion with an IA system and how you try to estimate nitrogen removal from an IA system. Because in a urine diversion system, you can measure the actual nitrogen concentration, which we did. It's around 5,000 or 6,000 milligrams per liter. That's a direct chemical analysis, so you can do it and you know that's accurate. And the number of gallons of urine you collect per house or per entire watershed, you can pool it. It doesn't really matter if you're trying to measure nitrogen removal in a watershed. You can just look at the total volume of urine you collected from the watershed and the total concentration, or the average concentration of all that urine, multiply those 2 measured numbers, directly measured numbers together, and get an actual pounds of nitrogen removed. So there's a direct calculation based on actual measurements that you can get. And so it doesn't matter if you're guessing correctly about how often people are home, how many people are actually in a house, is it seasonally occupied, is it year round? You can actually measure the urine removed and actually measure the concentration of nitrogen in the urine and find out how many pounds of nitrogen you removed from the watershed, which I believe is what people are trying to do on the Cape, is hit a target of nitrogen that is being removed. IA systems, on the other hand, have challenges in calculating this, and there's ways to try to overcome them, but it still is not as accurate. Because with an IA system, you characterize an IA system through testing, and several IA systems are set up and they're maintained properly, they're operating correctly, and you test the concentration in, the concentration out of that system, and you get a benchmark for how much nitrogen percentage-wise is removed from that system. Now that will vary if the operating systems change, but you use that benchmark because you need some estimate of what the real world operation is of an IA system. So there's the estimate for how much nitrogen would get removed. Then you have to estimate how many pounds of nitrogen are going into an IA system from a given home. And that can vary a lot because maybe there's a typical home, but in any individual home, the number of occupants will vary. How much they're at home will vary. Even what they eat will vary because how much protein you eat determines how much nitrogen is in your urine. How much food you eat determines how much nitrogen is in the urine. So there are all these factors that go together, and you have to just use an estimate for what a household is putting into their system. Then you multiply 2 estimates together to get an estimated removal rate. And I think you're telling me to wrap up. I'm on my final slide. So I think we're about done here. The closing thought on that, though, is just that there's a wonderful ability of urine diversion to exactly measure removed nitrogen, where IA systems have to estimate it, and that is a compelling aspect of this if you're biggest goal is to remove nitrogen from your watershed. So I will close there. And if you have any questions, you can also be in touch with Brian, who can be in touch with me. I'm available from 5 to 6 after this via the phone if anyone has longer follow-up questions.
And we have time now for questions too. That's why we're. So, question in the back there.
So, Abe, I understand the argument from a nitrogen perspective. I'm a little concerned on a municipal scale because of a cautionary tale about 15 years ago working in Maine with solids, and at that time, solids composting and land application was considered a really good thing. 15 years on now, some of those very fields we were using are now panicking because there's high PFAS concentrations. So the question I have for you is, has the center started looking at sort of second order potential problems coming from urine, not nitrogen?
Yes.
PFAS or hormone or CEC or whatever the next thing coming down the line is. And if you're looking at large scale land application, how's that involved in your quantification? Thank you.
Yes. Yeah, great question. And who was that from? I wasn't able to tell.
My name's Rob. I work for the town of Barnstable.
Rob
Great.
from the town. He works for the town of Barnstable.
Oh, great. Okay, great. Thank you, Rob. Yes, we have been studying pharmaceuticals and as well as PFAS. We have a 5-year study that is largely centered on PFAS, funded through the USDA, and we did some pharmaceutical studies funded by the EPA and the National Science Foundation. What we found for the pharmaceuticals was the pharmaceuticals are detectable in wastewater. They're detectable in the influent and the outflow and the effluent from a wastewater plant. So they are, ending up in surface waters, ending up in water that's used for irrigation as well. So they're in our environment from wastewater. We wanted to know what happened to the pharmaceuticals in urine if we used that urine to fertilize crops. And so we looked at the pharmaceuticals that were most abundant and most likely to be taken up by plants. And we determined that, for one thing, we didn't observe any accumulation of any of those pharmaceuticals in soil over the 3 years of that study. We did measure extremely low levels of the pharmaceuticals in crops, but it was the order of where you'd have to eat over 3 million salads made from the lettuce we grew to get a single therapeutic dose of, say, the Tylenol or the acetaminophen or the ibuprofen or like a cup of coffee's worth of caffeine. So it was detectable at minute levels, but it would take many, many human lifetimes to actually get any appreciable amount of those pharmaceuticals. So that doesn't appear to be an issue. You can remove them using activated carbon, so that you can even go a step further, but it doesn't appear to be necessary. Also, there's nothing saying you have to use this on food for human consumption. It can be used for hay, it can be used for non-food crops. So there's a lot of different tacks you can take. The pharmaceuticals don't seem to be an issue. PFAS is a huge issue in wastewater and in sludge and biosolids particularly. We haven't published this yet, but one thing that we've uncovered in our research so far is that the amount of PFAS that comes down in rain is actually higher than the amount of PFAS that could reasonably be found in urine. What I mean to say is, if you fertilize a field with urine for a year, the amount of PFAS that could be in that urine, even if it was from highly exposed people who are exposed to contaminated PFAS water, the amount of PFAS in that urine would be less than the amount of PFAS that comes down in the rainwater on that acre of farmland over the course of the year. So PFAS is a big issue, but urine is not a significant source of that PFAS.
Other questions? Good. All right. Well, thanks, Abe. This was really good to see what other communities have, way ahead on getting infrastructure and things, and what possibilities there are. So really appreciate you doing this presentation today.
Thank you for giving me the opportunity to be here, and I would love to take any other questions or follow-up conversations that might be on people's minds.
Looks like we have a leaf breaking.
Do you think the PFAS is in the solids, or they're just undetectable?
Did you hear the question?
Sorry, I didn't. Could you repeat?
Do you think the PFAS is in the solids, or it's just undetectable?
Like in the solids of like feces?
Yes.
Yeah.
Yeah.
We have not looked at that yet, but I do know that as a sort of like a guiding principle, the sources of PFAS in sludge, as I understand it, just from reading other people's papers, is that it's largely from industrial inputs, from firefighting foams, from waterproof clothing, from some food packaging has been made with PFAS that's being phased out. But I think that the human body is that's the sink for that's where PFAS ends up, where we especially don't want it, is when it gets into the human body. But the human body isn't the source of it, and our food is not necessarily the source of it. I think it is to some degree. PFAS is everywhere, and I'm not a PFAS expert. I'm more knowledgeable about PFAS as it affects urine. But yeah, just my somewhat informed understanding is that the PFAS in wastewater, there are a lot of known major contributors that are like that can be controlled. Sorry, I'm going to stop talking because, as I say, I'm not an expert on this, and I just have some ideas, but not some hard facts.
Thank you.
All right. Thank you.